Now that we've taken a good look at probability and a good look at matrices, we're going to bring the two together and look at how we can use matrices to help us calculate some probabilities. We're going to start with these things that are called Markov chains. Now, a Markov chain is a sequence where an outcome depends on the previous outcome. It's almost as if to say we have a chain of events, that every result is a result of the previous result, which is a result of the previous result. So let me just kind of set up an example of what we mean by this. Let's say we have two insurance companies. We're going to call them Insurance A and Insurance B. A and B. Each month, 20% of the A customers switch to B, and 15% of B customers switch to A. In order to model this situation, what we are going to do is we are going to develop what is called a transition matrix. That tells us how to transition from one month to the next month. So we use the letter T always to represent the transition matrix. And to just kind of label the rows and columns, we're going to use the rows to represent this month. This month, they're either a customer of A or a customer of B. Setting up our matrix. Then the columns are going to represent next month. Next month, they will either be a customer of A or a customer of B. What we are told is 20% of A switch to B. So in A, 20% of this month's A's are going to be B's next month. And so right there, that's where the 20% probability is going to go, which we can represent with 0.2. So this month A becomes next month B 20% of the time, which means they stay as A customers 80% of the time. Similarly, we are told that 15% of the B customers switch to A. So a B customer is going to switch to A next month 15% of the time. So in the B to A, we have 0.15. Then for the final entry, B to B, staying with B, is the complement of that, 1 minus 0.15, or 0.85. And so we can see from this matrix how they transition from this month to next month. If I am a B customer, there is a 15% chance I'll switch to A, and an 85% chance I'll switch to B. If I'm an A customer, there's an 80% chance I'll stay with A, and there's a 20% chance I'll switch to B. That's what the transition matrix does, is it shows us how to move from one month to the second month. So if that's how we go from the first month to the second month, what happens then with the third month? Well, to set this up, we can do this one of two ways. The old way we used to do this from our previous unit is we would set up a tree. We would say you could be with A, And from A, you could switch to either A or B. And then from A, you could switch to either A or B. From B, you could switch to either A or B. Or you could have started with B to begin with. We don't know where you started. And you could go to either A or B. And then in the third month, you could go to either A or B. To either A or B. And we can assign probabilities to each of these branches. Using our matrix up above to go from A and staying with A staying with A happens 0.8% of the time. So from A to A is 0.8. From A to B is 0.2. Similarly, from B to A happens, B to A is this guy over here. B to A happens 0.15 of the time. B to B is 0.85. And then we kind of repeat this pattern. From A to A, in the middle now, going from A to A, we know that happens 0.8 of the time. A to B happens 0.2 of the time. B to A happens 0.15. And B to B happens 0.85. Same thing in the second half. A to A happens 0.8. A to B happens 0.2. B to A happens 0.15. And B to B happens 0.85. And then we can calculate the probability of any result by multiplying down the line. So just starting at the top, 0.8 times 0.8 is 0.64. 0.8 times 0.2 is 0.16. 0.2 times 0.15 is 0.03. 0.2 times 0.85 is 0.17. 0.15 times 0.8 is 0.12. 0.15 times 0.2 is 0.03. And 0.85 to 0.15 is 0.1275. And 0.85 times 0.85 is 0.7225. And if we want to know from the beginning to the end what these are, this first entry started with A and ended with A. That is an A to A entry. The next one started with A and ended with B. The next one started with A and ended with A. Granted, we did B in the middle, but that doesn't matter. We know where we start and where we end. The next one starts with A and ends with B. Then, the next one started with B, ended with A. Then there's a started with B, ended with B. Then we have started with B, ended with A, and started with B, ended with B. That kind of puts us into 4 groups, really. There's start with A and end with A. Happen 0.64 here, start with A, end with A. 0.3 there. The second group started with A and ended with B. Starting with A and ending with B. There's 0.16 and 0.17. The next group started with B and ended with A. 0.12 and the 0.1275. Started with B, ended with A. And finally, starting with B and ending with B is 0.3 and 0.725. So we've got 4 groups that represent the 4 cells of our transition matrix. To go from A to A, we have the 0.64 plus the 0.03. That happens 0.67 of the time. In blue, from A to B, we had a 0.16 plus a 0.17. That happens 0.33 of the time. in green to start with B and go to A. From B to A, that was 0.12 plus 0.1275. That's going to be 0.2475. And in pink, going from B to B, that's 0.03 plus 0.7225 is going to be 0.6525. Oops, 0.75, sorry. 0.7525. Now, this was a lot of work to figure out the third month. It would be great if there was an easier way. In fact, there is. Remember that transition matrix T we had? T took us from the first month to the second month. If we do that twice, if we go T, that takes us from one month to the next, and multiply it by T, that takes us to the next month. Essentially, we're finding T squared. That will give us the same information this time for the third month. So similar to the first matrix we had with this month and next month, now it's going to be this month and third month, starting with A or B and ending up with A or B. We're going to do this on our calculator, so first we need to program in the transition matrix to our calculator. To put the transition matrix in our calculator, we'll go second matrix and over to edit. And our transition matrix is a 2 by 2 matrix with entries of 0.8, enter, 0.2, enter, 0.15, enter, 0.85, enter. And we'll hit second, quit. I like to put the matrix on my screen to make sure I typed it in right. Yes, that is the correct matrix. So in order to get to the third month, we need to take matrix A. So we go to matrix A, and we are going to multiply it by itself. We're going to take matrix A squared, just like we're doing down here. The transition matrix squared. And when we hit enter, we get these values. We get 0.67, 0.67, 0.33, 0.2475, 0.2475, and 0.7525. Notice the movement from A to A is exactly what we found doing the tree. The movement from A to B is exactly what we found from the tree. The movement from B to A is exactly what we found from the tree. And again, the movement from B to B is exactly what we found from the tree. This matrix gets us the same result as the tree, but with a lot less work. The calculator really is doing all the hard work. The big thing that I want to notice as we do this, as we get to more involved problems here in just a second, the exponent is always 1 less than the final month. 1 less. Because the original matrix, the first matrix, goes from 1 to 2. The second matrix goes from 1 to 3. So the exponent is 1 less than the goal. So if I want to know what happens after 1 year with this company, that's 12 months, we just take the transition matrix to the 11th power. Again, the exponent is 1 less than we're looking for. That takes us from this month, A and B, to 12 months, or 1 year, A and B, to find out how much of the market each one is going to have. So on the calculator, we're going to do second matrix, A, and we said we wanted to do the matrix to the 11th power. A to the 11th power is this guy. Copy him down. I'm going to move him over. 0.4336. 0.4336. Below that is 0.4248. 0.4248. And then if we scroll to the right, we can see the last entry, 0.5664, 0.5664, and 0.5752. 0.5752. This tells us that after a year, A's customers, 43% will still be with A. 57% have switched to B. Of B's customers, 42% have switched to A. And of B's customers, 58% have stayed with B. Whoops. Took away too much there with that eraser. So that's what this matrix tells us, is the probability of where a customer will be after so many months. And what you might notice is these numbers between A and B are getting close to each other. Notice 0.43 and 0.42 are really close to each other. 0.56 and 0.57 are really close to each other. And that's not an accident. Actually, over time, they are going to reach what is called equilibrium. Let's look at what happens after 6 years. 6 years, 6 times 12 is 72 months, which means we need to take our transition vector to the 71st power, one less, to look at this month, A and B. 6 years, A and B, to find out what the market share is. So on our calculator, we're going to do second matrix, A, and we're going to raise it to the 71st power. Hit enter. Notice when we went all the way to the 71st power after 6 years, the first and second rows are exactly identical. In fact, we can figure out what fraction those identical things are if we hit math and 1 for fraction. It's going to give us those values as fractions, 3/7 and 4/7. 3/7 and 4/7. And the second row is exactly identical, 3/7 and 4/7. When they hit this equilibrium where they are exactly the same, this tells us how much of the market each one of these companies will have in the long run. It tells us that A will have, looking at A's column in 6 years, A has 3/7 of the market share. And B will have, going down B's column in 6 years, 4/7 of the market in the long run. And what's really interesting is if we look at this market share as a vector, what we'll call the probability vector, Actually, let me just name it. It is a fixed probability vector. Also called the equilibrium vector. If we can find what this equilibrium vector is and multiply it by the transition matrix, we will get the same equilibrium vector back. Another way of saying this is if we take the transition matrix to some huge exponent, I'm going to say infinity, we will get the equilibrium vector in each row. That shows how much of the market share each company has in the long run. So, for the example we're looking at, we found that the equilibrium A has 3/7 of the market share. B has 4/7 of the market share. If we were to multiply that by the transition matrix that we've been playing with this whole time of 0.8, 0.2, 0.15, and 0.85, it should equal the same equilibrium vector. Basically what we're looking at is the share of the market by how the market changes when it's at equilibrium will give you the same share of the market. And this only happens in equilibrium. If we pick any other values besides 3/7 and 4/7, the change will give us a new share of the market. However, if we repeat this over and over again, you will always go to equilibrium. Let's look at it on the calculator. We'll go second matrix. I'm going to edit a new matrix. We're going to call it matrix B. It's going to be this equilibrium vector. It's got one row, enter, with two columns. Whoops. One row, enter, two columns, enter. And it's 3/7 for the first entry, 4/7 for the second entry. When we hit second quit, we take the equilibrium matrix, that's matrix 2, the 1 by 2, and we multiply it by the transition matrix, which we had in matrix 1, written as a fraction. You see we get the same matrix again, 3/7 and 4/7. 3/7 and 4/7. Once A has 3/7 of the market, it will always have 3/7 of the market. Once B has 4/7 of the market, it will always have 4/7 of the market. Now that might bring up an interesting question. Because capital B now, off the Markov chain definition, is when we're finding the equilibrium. We say that Markov chain can reach equilibrium if some power of the transition matrix of T has only positive entries. That means no zero, no negative. Now granted, we're talking about probabilities, so we're not going to see any negative entries, but specifically no zero is the big thing. So, for example, if I have a transition matrix that is equal to 1, 0, 0.3, 0.7, if I can find some exponent of this transition matrix that has all positive entries, we can reach equilibrium. So let's try it. We'll go to Matrix, over to Edit. We're going to edit, we'll change A to a 2 by 2 matrix again, with entries of 1, 0, 0.3, 0.7, second quit. And we'll put matrix A on the screen, 103.7. Now if we raise that to some large exponent, if we just hit the exponent button, it'll do it to the previous matrix. Let's say we take it to the 50th power. And let's see if we can do fractions. Might not let us do fractions. No, there's no fraction for this. But what I want to notice is the top right entry is still 0. If we took t to some large exponent, you are going to have some number, a 0, some number, and another number. I'm going to call them A, B, and C. But the important thing is that 0 in the top right corner never disappears. So we don't know if this is going to reach equilibrium or not. We're going to say no equilibrium. Contrast that then with a transition matrix that's equal to, what if we put the 0 in the top left? 0, 1, 0.5, and 0.5. Now if we program that matrix in as a 2 by 2 matrix with 0, 1, 0.5, 0.5, second quit, second matrix A, I like to put it on the screen first to make sure I typed it in right. If I even square this matrix, take the previous answer and square it, we get all positive non-zero entries, 0.5, 0.5, 0.25, and 0.75. So t squared equals 0.5, 0.5, 0.25, 0.75. And because we have all non-zero entries, we can reach equilibrium. We still don't know what equilibrium is, but we know we can reach it. Now, how do we find it? Well, it's really easy to find the equilibrium vector on a 2 by 2 matrix, because the equilibrium vector is going to represent the two values. Let's say we don't know the first value, but the second value has to be everyone else. It's the complement of the first value, so we really just have to take 1 minus the equilibrium. And we know if we multiply that by the transition vector, it's going to equal the equilibrium times 1 minus the equilibrium. Because the equilibrium times the transition equals the equilibrium. We can use this to help us solve. So, let's say, for example, we have a transition matrix that's equal to 0.25, 0.75, 0.83, and 0.17. We want to know what the equilibrium is. Well, we don't know what E and 1 minus E is, but we do know that's the form of the equilibrium, times 0.25, 0.75, 0.83, and 0.17. And that's going to equal the equilibrium and 1 minus the equilibrium, because the equilibrium times the transition will always equal the equilibrium. Well, we're multiplying two vectors, so we're going to multiply a row times a column. When we do that, we get 0.25e plus 0.83 times 1 minus e. Then we get to multiply a row times a column for the second entry, which gives us 0.75e plus 0.17 times 1 minus e. And that is still equal to our equilibrium vector of E1 minus E. This is actually going to give us equations that we can solve. I always like to pick the first entry must equal the first entry, right? So let's look at that. If the first entry must equal the first entry, then we could say 0.25e plus 0.83 times 1 minus e has to equal e. We could have also done the second entry has to equal the second entry. It gives us the exact same answer. So whichever one you want, usually the first is easier. So let's solve it. Distribute, we get 0.25e plus 0.83 minus 0.83e equals e. Combine like terms. We've got 0.25 minus 0.83 gives us negative 0.58e plus 0.83 equals e. Get the e's on one side by adding 0.58e. Remember, that's 1e plus 0.58 gives us 0.83 equals 1.58e. Divide both sides by the 1.58. And e equals, let's get rid of the decimal points by moving them twice, 83 over 158. Which means the other entry in the equilibrium is 1 minus e, or 1 minus 83 over 158. We need a common denominator. That's easy. That's 158 over 158. That equals 1. Minus 83 over 158. And we do that on our calculator. 158 minus 83 is 75 over 158. So the equilibrium vector is 83 over 158 and 75 over 158. So with this transition matrix, we reach equilibrium when the first group maintains 83 out of 158 of the market share, and the second organization has 75 out of 158 of the market share. This is our equilibrium. Now, speaking of market share, we can use these transition matrices to help us find out how much of the market share each company has. Let's say I have a transition matrix between three companies, A, B, and C. A, B, and C. And of A's customers, 50% or 0.5 stay with A, 30% switch to B, and 20% switch to C. Of B's customers, 20% switch to A, 70% stay with B, and 10% switch to C. Of C's customer, there's a probability of 0.1, they'll switch to A, 0.3, they'll switch to B, and 0.6, they will switch to C. We also know that the initial market share is 0.4, 0.2, 0.4. That means 40% of customers belong to A currently, 20% belong to B currently, and 40% belong to C currently. We can then calculate how this share is going to change over time. Let's say this is a 1-month change. So we've got this month and next month. So this transition tells us what happens to 1 month. And so let's look at the new share after 1 month. The way we do that is we can take the initial market share of 0.4, 0.2, 0.4, and multiply it by the transition matrix. 0.5, 0.3, 0.2, 0.2, 0.7, 0.1, 0.1, 0.3, 0.6. And that's going to equal our new market share of A, B, and C. So let's do that on the calculator. Second matrix. Over to Edit. We're going to do a 3 by 3 matrix. For matrix A, this is our transition matrix of 0.5, 0.3, 0.2, 0.2, 0.7, 0.1, 0.1, 0.3, 0.6. So A is the transition matrix. Then we'll go over to matrix and edit a 1 by 2 matrix. Actually, it's a 1 by 3 matrix. B is going to be our market share of 0.4, 0.2, 0.4. We'll hit second quit. And so we need to multiply B, the transition matrix. The order is important. B, the transition matrix, times A. I think I said that wrong. We need to multiply B, which is the market share, times A, which is the transition matrix. And when we do, we get 0.28, 0.38, 0.34. 0.28, 0.38, 0.34. So after 1 month, B seems to have taken the lead. A has 28% of the market, B has 38% of the market, and C has 34% of the market. And we can start to see what's happening to the market over time. Let's look at the share after 1 year, which is 12 months, right? Same exact idea. We take the initial market share, always go back to the initial market share of 0.4, 0.2, 0.4, and we're going to multiply by the transition matrix of 0.5, 0.3, 0.2, 0.2, 0.7, 0.1, 0.1, 0.3, 0.6. But we need to do that transition matrix 11 times. Remember, 1 less than the number of months, 11 times. So B was our initial market, times, we're going to do the transition matrix, which we put into A. We're going to do that 11 times, so we'll use the exponent key above the divide 11 times. And we get, let's just round this to 4 decimal points like we've been doing with percentages and probabilities. 0.24, oh, it's going to round up to 0.25. So 0.25, that's A. B, oops, I went past B. B is 49998. So that's going to actually round up to 0.5. B is going to have about 0.5 of the market share. And C, 0.2500, so that's just 0.25. So after 1 year, A has 1/4 of the market share, approximately. B has 50%, and C also has 25%. And we can use this idea to find the long term market share. And basically what we want to do there is take our initial vector, 0.4, 0.2, 0.4, our initial matrix of the market share, times the transition of 0.5, 0.3, 0.2, 0.2, 0.7, 0.1, 0.1, 0.3, 0.6, and we need to basically do that an infinite number of times. Well, our calculator doesn't have infinity, but we can pick a large exponent and see if it works. So we'll hit second matrix. We want B first, times matrix A to some very large power, maybe 1,000 power. That's probably sufficiently large. Whoops, too large. Well, let's do 100th power then. And we see that over the long term, we do hit these exact decimals that we were rounding to after a year, 0.25, 0.5, and 0.25. And we can express those as fractions. With your calculator, you know you've reached your equilibrium, your long-term value, if we can write them as fractions. If you ask for a fraction and your calculator gives you a decimal, it means you're not there yet. You haven't reached that equilibrium. But here we have at 1/4, 1/2, and 1/4. So unless something changes the market, A will have 1/4 of the customers, B will have half the customers, and C will have 1/4 of the customers. This is how we can use Markov chains, where one outcome depends on the previous outcome, to make predictions about how the market is going to change over time and how it will reach a final equilibrium. Take a look at the homework assignment, come to class with questions, and we will see you tomorrow.